Picture a pair of galaxies locked in an elegant, slow-motion embrace, their spiral arms stretching across the void like celestial brushstrokes on the darkest canvas imaginable. This isn't destruction, it's creation on a scale so vast it defies human imagination. Across the universe, galaxies don't just crash into one another, they weave together, trading stars, gas, and dust in a cosmic dance that can last billions of years. The result, breathtaking sculptures of light and matter, each collision unique, each merger a masterpiece written in the language of gravity. What makes these encounters so extraordinary isn't just their scale, it's the way they transform everything they touch. When galaxies collide, they don't simply shatter or fade away. Instead, they rebirth themselves, triggering explosions of new stars, forging unimaginable shapes, and sometimes even giving rise to entirely new galactic structures. Take the antennae galaxies, for example, two spirals caught in a gravitational tango, their long tails of ejected stars stretching hundreds of thousands of light years into space. Or consider the mice galaxies, their twin tails whipping through the cosmos like celestial comets. These aren't accidents of nature, they're proof of the universe's endless creativity. And here's the most astonishing part. This isn't just happening in some distant corner of the cosmos. Our own Milky Way is on a collision course with the Andromeda galaxy, a slow-motion merger that will rewrite the night sky for any future civilizations. But don't worry, this isn't a story of chaos. It's a story of transformation, of how the universe constantly reinvents itself through these grand, gravitational ballets. Over the next few minutes, we'll unravel the secrets of these cosmic collisions, from the way they spark dazzling bursts of star formation to the mysterious forces that shape their final forms. So sit back, look up, and let's explore the artistry of galactic collisions where the universe itself becomes the artist. Think of the universe as a grand ballroom, where galaxies glide through space not as solitary guests but as partners in an endless, graceful dance. Their interactions are governed by gravity's invisible hand, sometimes a gentle pull, other times an irresistible force drawing them into an intricate cosmic waltz. Take the Whirlpool galaxy, for instance, its delicate spiral arms stretched and twisted by the gravitational embrace of a smaller companion galaxy. This isn't a violent clash, it's a slow, mesmerizing exchange of energy and matter, like two dancers trading momentum as they spin across the floor. What's truly remarkable is how these interactions unfold over timescales that dwarf human history. A single galactic encounter can take hundreds of millions of years to play out, with each phase revealing new wonders. First comes the initial approach, where tidal forces begin to sculpt the galaxies, warping their shapes into long, luminous arcs. Then, if the dance continues, gas and dust are pulled into swirling bridges between them, igniting bursts of star formation that light up the cosmic stage. And in the most dramatic cases, like the iconic mice galaxies, the gravitational pull becomes so intense that the galaxies stretch into spectacular tails of stars, streaming behind them like celestial ribbons. Yet even in these extreme encounters, individual stars rarely collide. The vast distances between the mean galaxies pass through one another like ghosts, their stellar inhabitants undisturbed even as their collective structures are reshaped. It's a paradox of scale. These events are both cataclysmic and delicate, destructive and creative all at once. The aftermath often leaves behind something entirely new, a merged galaxy with a unique identity, bearing the scars and splendors of its past. And this dance isn't just a spectacle, it's a driving force behind galactic evolution. Without these interactions, many galaxies would remain static, their gas reservoirs untouched, their star-forming potential untapped. It's through these gravitational encounters that the universe stirs the cosmic pot, mixing ingredients to create the diversity of galaxies we see today. From the stately ellipticals to the fiery starburst galaxies, each owes its existence in part to the ballet of collisions and near misses that have shaped them over billions of years. So the next time you gaze at a galaxy in the night sky, remember, it's not an isolated island in the cosmos. It's a dancer in the grandest performance of all, moving to rhythms set in motion by gravity itself. And as we'll see, some of the most stunning galactic transformations are still to come, including one that will reshape our own corner of the universe. At first glance, space might seem like a cold, empty void where nothing changes, but look closer, and you'll witness the universe's most patient artists at work. When two galaxies begin their gravitational tango, the first strokes of their cosmic masterpiece appear almost imperceptibly. Like a sculptor's hands shaping clay, gravity starts to mold their forms, gently at first, pulling stars and gas into delicate arcs that stretch across the darkness. The galaxies don't slam together, they inch closer over millennia, their mutual attraction warping their structures in ways both subtle and spectacular. Take the mice galaxies, suspended in the cosmos like a pair of dancers caught mid-twirl. Their spiral arms, once neat and symmetrical, now stream behind them in long, luminous tails, some stretching over 300,000 light-years. These tidal tails aren't just debris, they're trails of stars and gas pulled free by the relentless tug of gravity. And it's not just the outer regions that transform. Deep within each galaxy, vast reservoirs of interstellar gas begin to shift, swirling into bridges between the two, as if the universe itself is sketching the first lines of a new creation. What's mesmerizing about this phase is how slow and deliberate it is. A single pass between galaxies can take tens of millions of years, with every gravitational nudge leaving its mark. The forces at play are so immense, yet the changes unfold with a kind of cosmic elegance. Spiral arms that once traced perfect curves now flare outward, their shapes distorted into ethereal plumes. Star-forming regions, once quiet, ignite as compressed gas collapses into newborn suns, painting the galaxies with bursts of blue-white light. Even the dark, dusty lanes within them are reshaped, twisted into new patterns by the invisible hand of gravity. But here's the twist: despite the chaos, the galaxy's stars rarely collide. Space is so vast that even in a head-on merger, solar systems pass like ships in the night, undisturbed. It's the galaxies themselves, their gas, dust, and overarching structures that bear the brunt of the transformation. And as the dance continues, the bridges between them grow thicker, the tails longer, and the stage is set for the next act, a fiery burst of stellar birth that will redefine both galaxies forever. As the galaxies spiral closer, gravity's grip tightens, and the dance takes a dramatic turn. What began as a delicate distortion now erupts into a fiery spectacle of creation and chaos. The space between them crackles with energy. Vast clouds of gas, once drifting peacefully, now collide and compress under unimaginable pressure. Like striking a match in the cosmic dark, these compressed pockets ignite, lighting up the galaxies with the brilliant blue-white glow of newborn stars. It's as if the universe itself has flipped a switch, transforming these colliding giants into dazzling stellar nurseries. Nowhere is this more breathtaking than in the antennae galaxies, two spirals so entwined they've become a single, turbulent masterpiece. Their cores, once distinct, now swirl together like ink dropped into water, while twin rivers of stars, each hundreds of thousands of light years long, arc outward in opposing directions. These tidal tails, studded with star clusters and glowing nebulae, are the galaxy's way of rewriting themselves in real time. The violence of the encounter isn't destruction, it's rebirth. Every shockwave rippling through the gas, every gravitational jolt, forces the galaxies to shed their old forms and embrace something entirely new. Yet amid this cosmic upheaval, there's a strange kind of order. The chaos isn't random, it follows the unbreakable laws of physics, shaping the galaxies with mathematical precision. Dense knots of gas collapse into star clusters, their light so intense it outshines entire galaxies. Supernova explosions ripple through the interstellar medium, scattering heavy elements that will one day form planets and perhaps life. Even the galaxy's original spiral arms, now stretched and twisted beyond recognition, become canvases for gravity's artistry, their curves warped into surreal, luminous tendrils. What's astonishing is how fleeting this stage is on a cosmic scale. These fireworks of star formation, though lasting millions of years, are just a brief chapter in the galaxy's long evolution. The very forces that ignite them also sow the seeds of their eventual calm. As the gas is consumed in stellar furnaces or blown away by fierce stellar winds, the frenzy of creation will slow, leaving behind a galaxy forever changed. But for now, in this moment of celestial intensity, we're witnessing the universe at its most creative, a reminder that even in chaos there's beauty, and in collision there's transformation. And this isn't just happening in some far-off corner of space. The same processes that sculpt the antennae galaxies will one day unfold right here when the Milky Way and Andromeda meet. Their close encounter, though billions of years away, will ignite similar bursts of star formation, painting our future sky with light. Until then, we have front-row seats to the universe's grandest show, where galaxies don't just collide but evolve, telling a story written in stardust and gravity. The grand finale of this cosmic ballet arrives when the galaxies, once separate, finally surrender to gravity's embrace and merge into one. Picture two whirlpools of stars and gas, their spirals now unrecognizable, swirling together in a final, breathtaking act of unification. This isn't a tidy process, it's a gravitational storm where stars are hurled into chaotic new orbits and vast streams of gas collide, ignite, and settle into a single, majestic structure. The result, often a smooth, featureless elliptical galaxy, its once distinct spiral arms erased by the violence of the merger. These cosmic behemoths, like Messier 87 with its towering jet of plasma, are the quiet tombstones of ancient collisions, their serene appearances belying the fiery origins that shaped them. But the drama doesn't end with the stars. Deep within the merging galaxies, their supermassive black holes, each millions or even billions of times the mass of our Sun, begin a deadly spiral toward one another. Drawn together by friction and gravity, they orbit faster and faster, churning the surrounding space-time until, in a final cataclysmic moment, they collide. The impact sends ripples through the fabric of the universe itself, gravitational waves first predicted by Einstein that radiate outward at the speed of light. These waves, detected by observatories like LIGO, are the universe's way of whispering the secrets of its most violent events. Yet amid this chaos, there's a strange harmony. The merger doesn't just destroy, it rebuilds. Stars flung into wild orbits eventually stabilize, tracing new paths in the combined galaxy's gravitational field. The gas, once turbulent, settles into a calmer, more diffuse state, its star-forming frenzy spent. Even the black holes, now merged into a single, more massive monster, become the anchor for a new galactic core. The legacy of the original galaxies lives on in this reborn structure, their histories written in the motions of their stars and the chemistry of their gas. And this isn't some rare cosmic spectacle. Elliptical galaxies, which outnumber spirals in the densest regions of the universe, are nearly all products of past mergers. Their smooth, rounded shapes are the fingerprints of collisions that occurred billions of years ago, a reminder that the universe is constantly recycling itself. Even our Milky Way bears the scars of smaller mergers, dim streams of stars winding through its halo, the ghosts of dwarf galaxies long since consumed. So when you look up at the night sky, remember, the galaxies you see aren't static islands. They're dynamic, ever-changing entities shaped by collisions that unfold over cosmic time. And one day, far in the future, the Milky Way and Andromeda will complete their own merger, leaving behind a single, brilliant elliptical galaxy, a testament to the universe's unending dance of destruction and creation. Stretching across the cosmos like luminous ribbons, tidal tails are the universe's most breathtaking signatures of gravitational artistry. These vast, sweeping arcs of stars and gas, some longer than the Milky Way itself, are sculpted by the same forces that gently tug ocean tides on Earth, but on a scale so immense it defies comprehension. When galaxies brush past one another, their gravitational pull doesn't just warp their shapes. It plucks material from their edges, flinging it into space in radiant, slow-motion arcs. The Tadpole Galaxy offers one of the most dramatic examples, its tail trailing over 280,000 light-years behind it, a glittering river of stars born from the chaos of collision. But these tails aren't merely debris, they're cosmic crucibles. As gas and dust are ripped from their parent galaxies, they compress along these stellar highways, triggering bursts of star formation that dot the tails with brilliant blue clusters. Imagine a painter flicking droplets of light across a dark canvas, each cluster a newborn stellar city, glowing with the intensity of youth. The antennae galaxies take this phenomenon even further, their twin tails sparkling with so many young stars that they outshine the galaxies themselves. It's a paradox. The very forces that tear galaxies apart also seed them with new life. What's even more remarkable is how these structures endure. Tidal tails aren't fleeting features. They can persist for hundreds of millions of years, slowly fading as their stars drift apart or return to their reshaped galactic homes. Some, like those of the mice galaxies, become so elongated they resemble celestial comets, their tips eventually dissolving into the intergalactic void. Yet, even as they fade, they leave behind a legacy clusters of stars that may one day be absorbed into new galaxies, carrying with them the chemical fingerprints of their violent birth. And here's the twist: these tails aren't just relics of destruction. They're proof of the universe's relentless creativity. Without galactic collisions, many of the star clusters we see today, perhaps even our own solar system, might never have formed. The same gravitational chaos that stretches galaxies into surreal shapes also stirs the cosmic pot, mixing primordial hydrogen with heavier elements forged in stellar furnaces. It's a cycle as old as time, chaos giving rise to order, destruction birthing creation. So the next time you see an image of a galaxy with a luminous tail, remember, you're not just looking at a collision. You're witnessing the universe paint its masterpiece. Starburst galaxies are the universe's most spectacular fireworks, shows cosmic beacons where star formation ignites with such ferocity. They outshine entire galaxies. Imagine a celestial factory where gas clouds, squeezed by the immense gravitational forces of colliding galaxies, collapse into stars at a breakneck pace. While a typical galaxy like our Milky Way might produce 1 or 2 new stars per year, starburst galaxies defy the norm, birthing hundreds, sometimes thousands, of stars annually. The Cigar Galaxy, also known as Messier 82, is a prime example, its core so densely packed with young, blazing stars that it glows with an intensity visible across millions of light years. What makes these galaxies so extraordinary isn't just their speed, but the sheer scale of their creativity. When two galaxies merge, their interstellar gas, normally spread thin, gets funneled into turbulent, dense pockets. Like logs thrown onto a fire, these compressed clouds ignite with stellar birth, lighting up the galactic center in a frenzy of blue-white light. The stars born in these explosions aren't just plentiful, they're also massive, burning hot and bright before ending their lives in supernova that scatter heavy elements across the cosmos. It's a chain reaction. Each explosion triggers new waves of star formation, creating a self-sustaining cycle of creation and destruction. But this brilliance comes at a cost. Starburst galaxies are cosmic shooting stars, dazzling but short-lived. Within just tens of millions of years, they exhaust their gas reserves, their stellar nurseries running dry as the last of their raw material is either turned into stars or blown away by the fierce winds of those same young stars. The Cigar Galaxy's dramatic outburst, for instance, won't last forever. Already, jets of superheated gas stream from its core, a sign that its star-forming days are numbered. Yet, even in their decline, these galaxies leave behind something remarkable, a new generation of stars, each carrying the chemical legacy of their explosive birth. And here's the twist: these starbursts aren't just isolated events. They're a critical chapter in the story of galactic evolution. The heavy elements forged in their fiery cores, carbon, oxygen, iron, become the building blocks for future stars, planets, and perhaps even life. Without these violent, luminous episodes, the universe as we know it would be far poorer, its galaxies missing the diversity of elements that make worlds like ours possible. So while the fireworks fade, their echoes linger, written into the fabric of every star that follows. At the core of every galaxy, hidden in the swirling depths of stars and dust, lurks a gravitational monster, a supermassive black hole. These cosmic behemoths, weighing millions or even billions of times more than our Sun, are the silent architects of their galactic homes. But when two galaxies collide, their black holes don't simply coexist. They engage in a duel of unimaginable scale, a battle fought not with light or fire, but with the invisible fabric of space-time itself. Picture two black holes, each the heart of its own galaxy, now locked in a slow, inescapable spiral toward one another. As they draw closer, their immense gravity distorts the space around them, creating ripples, gravitational waves that race outward at the speed of light. These waves, first detected by humanity in 2015, are the universe's way of announcing the final moments of this cosmic showdown. But before the black holes merge, they often stage a dazzling, if invisible, performance. Gas and dust, caught in their gravitational tug-of-war, swirl into vast, superheated disks around each black hole. Friction heats this material to millions of degrees, causing it to glow with intense X-rays and gamma rays. For a time, the galaxy hosts not one, but two active galactic nuclei, twin lighthouses of radiation that can outshine all the stars in the galaxy combined. The spectacle doesn't end there. As the black holes continue their dance, they fling stars out of orbit, warp the paths of nearby gas clouds, and even alter the very shape of their host galaxy. Some scientists believe these dueling black holes may be responsible for quenching star formation in certain galaxies, their fierce radiation and gravitational chaos preventing new stars from forming. Yet, paradoxically, they can also trigger bursts of star birth in other regions, their turbulent energy compressing gas clouds into stellar nurseries. And then, in a final, cataclysmic moment, the two black holes merge. The collision releases a burst of gravitational waves so powerful it briefly outshines the entire universe in gravitational energy. The resulting black hole, now even more massive, recoils from the impact, sometimes hurtling through its galaxy at speeds of thousands of kilometers per second. This recoil can leave the galaxy without a central anchor, its stars and gas drifting in new, unpredictable patterns. But the legacy of this duel isn't just destruction. The merged black hole becomes a new gravitational anchor, reshaping the galaxy's core and influencing its evolution for billions of years. The heavy elements forged in the surrounding maelstrom of radiation and shockwaves become the building blocks for future stars and planets. Even the gravitational waves rippling across the cosmos carry with them the story of this titanic encounter, a story written not in light, but in the subtle stretching and squeezing of space itself. So when we look at a galaxy, we're not just seeing stars and gas. We're witnessing the aftermath of an invisible war where black holes clash, merge, and ultimately redefine the destiny of everything around them. And somewhere in the depths of the universe, another pair of supermassive black holes is beginning its own deadly dance, a reminder that even in the darkest corners of space, the universe never stops moving, never stops creating. 4.5 billion years from now, the night sky will begin a transformation unlike any other in our galaxy's history. What now appears as a faint smudge of light, the Andromeda galaxy, will grow larger and brighter with each passing millennium until its spiral arms dominate the heavens. This isn't science fiction, it's an inevitable cosmic event written into the fabric of gravity itself. The Milky Way and Andromeda, drawn together by an unstoppable pull, will commence a dance that reshapes them both, not with destruction but with rebirth. Current simulations reveal the encounter will unfold in slow motion, a celestial ballet spanning hundreds of millions of years. At first, the galaxies will sweep past each other, their gravitational forces stretching their spiral arms into luminous tidal streams. Stars will be flung into new orbits, though the vast distances between them mean our solar system will likely remain unscathed. But the real spectacle begins as the galaxies loop back toward one another, their mutual gravity pulling them into an ever-tightening spiral. Over eons, their cores will draw closer, until finally, like two whirlpools merging into one, they coalesce into a single, colossal elliptical galaxy astronomers have nicknamed Andromeda. The night sky from Earth, assuming our planet still exists, will be unrecognizable. Andromeda's stars, once distant pinpricks, will mingle with ours, creating a dense tapestry of light. The familiar band of the Milky Way will vanish, replaced by a glowing, featureless haze as the new galaxy's stars settle into randomized orbits. Yet amid this upheaval, life could persist. The rarity of stellar collisions means planetary systems might survive intact, though their skies will tell a new story, one where the constellations we know today are lost to time. What's equally fascinating is how this collision mirrors events that have shaped the universe for billions of years. The Milky Way itself bears scars of past mergers, streams of stars winding through its halo, the remnants of dwarf galaxies consumed long ago. Even Andromeda shows signs of a violent history, its outskirts littered with stellar debris from earlier encounters. Our future merger isn't an anomaly. It's part of a grand cycle where galaxies grow, collide, and evolve. And while 4.5 billion years sounds impossibly distant, it's a reminder that the cosmos is never static. The universe we see today is just a snapshot in an endless reel of transformation, where even the mightiest galaxies are fleeting shapes in gravity's grand design. So when you gaze at Andromeda on a clear night, remember, you're looking at more than a neighbor. You're witnessing the future heart of our galaxy, a destiny written in the slow, silent pull of the cosmos. Among the most striking cosmic sculptures born from galactic collisions, Are ring galaxies structures so perfectly symmetrical they seem almost impossible in a universe ruled by chaos? Picture a stone dropped into a still pond, sending ripples expanding outward in flawless circles. Now imagine that same ripple effect, but on a galactic scale, where the stone is an entire galaxy piercing through the heart of another. The result is a celestial bullseye, a luminous ring of newborn stars radiating outward from a quieter core, a fleeting moment of order carved from the violence of impact. The Cartwheel Galaxy stands as the most iconic example, its brilliant blue ring glowing against the darkness like a cosmic fingerprint. Roughly 400 million years ago, a smaller galaxy sliced straight through its center, triggering a shockwave that hurtled through the cartwheel's disk at staggering speeds. This expanding wave compressed vast clouds of gas, igniting a firestorm of star formation along its leading edge. Today, the galaxy's outer ring blazes with the light of millions of young, massive stars, their intense blue hue betraying their youth. Meanwhile, the galaxy's original spiral arms, once stately and structured, now appear tattered, their patterns shredded by the gravitational disturbance. It's as if the universe paused mid-collision to sculpt this ephemeral masterpiece before the ring eventually fades into the galaxy's new, reshaped form. What makes ring galaxies so fascinating isn't just their beauty, it's the precision required to create them. Unlike messy mergers that twist galaxies into irregular shapes, ring structures demand a near-perfect head-on collision. The intruder galaxy must strike the larger one's center like a dart hitting a bullseye, sending a symmetrical shockwave racing outward. Even the angle of impact matters. A glancing blow might warp the disk into a lopsided arc, but only a direct hit can sculpt that perfect, luminous circle. Yet rings aren't permanent. Over hundreds of millions of years, the bright blue clusters along the ring's edge will age, their hottest stars burning out first, leaving behind a redder, dimmer glow. The ring itself will gradually disperse as gravity tugs its stars into new orbits, blurring the once sharp boundary into the galaxy's broader structure. The cartwheel's fate is already written. Its current splendor is just a brief chapter in a billion-year story of transformation. These rare galactic ripples remind us that chaos and order aren't opposites, they're partners in the universe's creative process. A single, precisely timed collision can birth a structure of breathtaking symmetry, proving that even in the vast, turbulent cosmos, there's room for fleeting perfection. And somewhere out there, another pair of galaxies may be aligning for their own fateful encounter, ready to paint the darkness with yet another luminous ring. In the grand theater of galactic collisions, the stars and gas we see are merely the actors, but the real director works from the shadows. Dark matter, invisible and mysterious, is the unseen force shaping every gravitational dance between galaxies. Though it emits no light and eludes direct detection, its gravitational pull is undeniable. Picture a galaxy not as a flat disk of stars, but as a vast, diffuse halo of dark matter, a cosmic scaffold that holds 10 times more mass than all the visible matter combined. When galaxies collide, it's these halos that first interact, their immense gravity dictating the trajectory of the entire encounter. Computer simulations paint a startling picture of dark matter's influence. As two galaxies approach, their dark matter halos stretch and warp, creating an invisible framework that guides the fate of the visible material. Tidal tails, those luminous arcs of stars we admire, are born from this hidden choreography. Without dark matter's gravitational grip, these spectacular features might never form. The Antennae galaxy's iconic tails, for instance, trace the paths carved by their colliding dark matter halos long before the stars followed suit. Even the final structure of merged galaxies, whether they become smooth ellipticals or retain some spiral features, is sculpted by how these halos intertwine. What's even more fascinating is how dark matter preserves a galaxy's identity during a collision. While stars and gas are flung into dazzling new configurations, the dark matter halo remains largely intact, a stable anchor amid the chaos. This explains why galaxies can pass through one another like ghosts, their stars scattering but their overall structures enduring. The Bullet cluster offers dramatic proof. When two galaxy clusters collided, their visible gas slowed and heated, but their dark matter, revealed by gravitational lensing, sailed straight through, leaving the visible and invisible components eerily separated. Yet dark matter's role isn't just about brute force. It's also a cosmic architect, enabling the universe to build the galaxies we see today. Without its gravitational scaffolding, the early universe's sparse gas might never have clumped together to form galaxies at all. Collisions would lack the dramatic transformations we observe. No starbursts, no tidal tails, no elliptical giants. The universe's artistry would be muted, its canvas less vibrant. So the next time you marvel at an image of colliding galaxies, remember, the beauty we see is just the surface. Beneath it all, dark matter pulls the strings, a silent maestro orchestrating the cosmos' most breathtaking performances. And as astronomers peer deeper into its mysteries, they're uncovering not just how galaxies collide, but how the universe itself is woven together. Galaxies, like cosmic predators, grow by consuming their smaller neighbors in a process as elegant as it is relentless. Galactic cannibalism isn't a chaotic free-for-all. It's a slow, methodical feast where larger galaxies strip stars, gas, and even dark matter from their smaller counterparts, absorbing them over billions of years. Take our own Milky Way. Its serene spiral arms and glowing disk hide a violent history of consumption. Wrapped around it like a faint, shimmering shroud lies the stellar halo, a graveyard of devoured galaxies, their stars orbiting in chaotic patterns that betray their foreign origins. One of the most dramatic examples is the Gaia Enceladus galaxy, a dwarf galaxy that once sailed through the cosmos independently before the Milky Way's gravity tore it apart. Today, its remnants live on as a population of ancient stars, swirling around our galaxy's outskirts in orbits tilted at odd angles. These stars are cosmic refugees, their chemical compositions distinct from the Milky Way's native population. They're richer in elements like alpha particles, a fingerprint of their origins in a smaller, faster-burning galaxy. By mapping their motions and chemistry, astronomers have reconstructed this galactic meal, dating it to roughly 10 billion years ago, when the Milky Way was still young and hungry. But the Milky Way's appetite didn't stop there. The Sagittarius dwarf spheroidal, a tiny galaxy discovered in the 1990s, is currently being unraveled like a celestial spool of thread. Each pass it makes around the Milky Way strips away more of its stars, stretching them into a looping river of light that wraps around our galaxy's poles. Even now, its core barely holding together continues to orbit, destined to dissolve entirely in another billion years. These mergers lack the fireworks of head-on collisions, but they're no less transformative. Like a sculptor adding clay to a masterpiece, each consumed galaxy leaves its mark, subtly reshaping the Milky Way's structure and chemistry. What's fascinating is how these quiet mergers drive galactic evolution. Large galaxies like ours didn't form in isolation, they grew by assimilating smaller neighbors, their gravity acting as a cosmic net that gathers scattered stars into a unified whole. Without this process, the universe might be filled only with tiny, fragile galaxies, their stars never coalescing into the grand spirals and ellipticals we see today. Even now, telescopes like Gaia are uncovering new streams of stars, ghostly remnants of past meals. each a clue to understanding how galaxies like ours came to be. And the Milky Way isn't unique. Andromeda, our nearest galactic neighbor, has an even more violent history, its outskirts littered with the shredded remains of dozens of smaller galaxies. In the distant future, when the Milky Way and Andromeda finally merge, their halos, already rich with the debris of past cannibalism, will mingle, creating a new, even larger galaxy built on the bones of its predecessors. It's a reminder that in the cosmos, growth isn't just about creation, it's about absorption, a cycle of destruction and renewal written in the stars themselves. Deep within the turbulent hearts of colliding galaxies, some of the universe's most violent and luminous events unfold hidden behind thick veils of cosmic dust. These are the ultra-luminous infrared galaxies, or ULIRG, celestial powerhouses so shrouded in debris that their brilliance is all but invisible to optical telescopes. Instead, they radiate with an intense infrared glow, a telltale sign of the chaos within. Imagine a bustling city cloaked in dense fog. The lights are still there, blazing brighter than ever, but you'd need heat-sensing goggles to see them. That's the paradox of ULIRG. They're among the brightest objects in the universe, yet they reveal themselves only in wavelengths our eyes can't perceive. At the center of this mystery lies ARP 220, a galaxy so luminous in infrared that it outshines a trillion suns. Born from the collision of two spiral galaxies, its core is a maelstrom of star formation and superheated dust. Every year, ARP 220 gives birth to hundreds of new stars, a staggering rate compared to the Milky Way's modest handful. But what makes ULIRG like this one truly extraordinary is their secrecy. The same dust clouds that obscure their light also absorb the furious energy of their starbursts, reheating and re-radiating it as infrared waves. It's as if the universe has wrapped these cosmic firestorms in a thick, glowing blanket, hiding their fury while amplifying their warmth. This phase of galactic evolution is both fleeting and transformative. ULIRG represent a galaxy's adolescence, a hyperactive, messy stage where mergers funnel vast amounts of gas into compact regions, igniting frenzied star formation. But the dust isn't just a byproduct, it's a key player in the drama. Without it, the intense radiation from newborn stars would blast their surroundings, quenching further star birth. Instead, the dust acts like a cosmic pressure valve, absorbing and redistributing that energy, allowing the galaxy to keep forging stars at a breakneck pace. Yet ULIRG don't last forever. Over tens of millions of years, the very stars they create will blow away the dust with powerful stellar winds, clearing the veil and revealing the galaxy's core. Some may even transition into quasars, their supermassive black holes feasting on the remaining gas and outshining the galaxy itself. Others will settle into calmer, more familiar forms, elliptical galaxies, perhaps their starburst days behind them. What's remarkable is how these hidden giants challenge our view of the cosmos. Before infrared astronomy, ULIRG were nearly invisible, their contributions to galactic evolution overlooked. Now we know they're critical players in the universe's story, shaping how galaxies grow, collide, and evolve. They remind us that the cosmos is full of secrets, waiting to be uncovered not by the light we see, but by the warmth it leaves behind. Beneath the visible chaos of colliding galaxies, an invisible force quietly shapes their destiny. Magnetic fields. These vast, intangible webs stretch across interstellar space, weaving through clouds of gas and dust like cosmic threads. While gravity dominates the grand choreography of galactic mergers, magnetism works on a subtler scale, guiding the flow of material and even determining where new stars can form. Imagine pouring iron filings near a magnet. The way they align along invisible lines mirrors how interstellar gas responds to galactic magnetic fields during collisions, channeling chaos into unexpected patterns. Recent observations of polarized light have given astronomers a glimpse into this hidden architecture. When light passes through magnetized gas, its waves align in specific directions, revealing the orientation of magnetic fields like a cosmic fingerprint. The Whirlpool Galaxy's collision with its smaller companion offers a stunning example. Its magnetic fields, once orderly, now twist in turbulent loops around regions of intense star formation. These fields don't just passively react to the collision, they actively shape it. Gas compressed by gravitational forces must also navigate this magnetic maze, slowing its collapse in some areas while accelerating it in others. The result, star formation becomes clumpy and uneven, with stellar nurseries igniting along magnetic highways, while other regions remain eerily quiet. What's fascinating is how these fields evolve during a merger. As galaxies intertwine, their magnetic lines stretch and tangle, amplifying in strength like rubber bands pulled taut. In the antennae galaxies, these amplified fields now guide colossal jets of gas, funneling material outward along precise paths and sculpting the iconic tidal tails. Meanwhile, deep within the collision zone, magnetic pressure can even counteract gravity, preventing some gas clouds from collapsing into stars altogether. It's a delicate balance: too much magnetism and star formation stalls, too little, and the galaxy's gas might dissipate into the void. Yet magnetism's influence doesn't stop there. These fields also act as cosmic accelerators, channeling charged particles into high-energy beams that radiate across the electromagnetic spectrum. Some merging galaxies, like Centaurus A, showcase immense magnetic bubbles around their cores, structures so powerful they launch jets of plasma at nearly the speed of light. Without these fields, the universe would lack some of its most energetic phenomena, from radio lobes stretching millions of light years to the mysterious cosmic rays that bombard our planet. So while gravity may set the stage for galactic collisions, magnetism fine-tunes the performance. It's the unseen hand that stirs the gas, directs the star formation, and occasionally rewrites the script entirely. And as astronomers peer deeper into this magnetic tapestry, they're uncovering a universe far more intricate than we ever imagined, one where even the emptiest spaces hum with invisible forces, quietly shaping the destiny of galaxies. Simulating the slow-motion dance of colliding galaxies isn't just guesswork, it's a triumph of modern astrophysics, where supercomputers act as cosmic time machines. Picture a virtual universe built from millions of lines of code, where every star, gas cloud, and dark matter particle obeys the unbreakable laws of physics. These simulations don't just recreate what we see through telescopes, they reveal the hidden mechanics behind galactic mergers, tracing paths that unfold over billions of years in mere weeks of processing time. The key lies in balancing complexity with precision, accounting for gravity's relentless pull, the turbulent swirl of interstellar gas, the explosive feedback of supernova, even the magnetic fields threading through it all. Take the iconic antennae galaxies, their tangled arms stretched across space like celestial brushstrokes. By feeding real observational data into simulations, astronomers can rewind the collision, testing how different initial conditions like the galaxy's angles, speeds, or gas content led to the structures we observe today. One groundbreaking simulation from the Artistry project traced their encounter back to a near-miss 700 million years ago, when gravity first stretched their spiral arms into those luminous tidal tails. Without these digital laboratories, we'd see only a snapshot frozen in time, missing the dynamic story behind the chaos. But simulations aren't just about the past, they're also our window into the future. When modeling the Milky Way and Andromeda's impending merger, researchers discovered a surprising twist. Their first close pass won't be the end. Instead, the galaxies will swing past each other like cosmic pendulums, their mutual gravity pulling them back for a second, even more dramatic collision. Only then will they fully merge into the elliptical behemoth we call Milky-Way. These predictions rely on painstaking adjustments, tweaking variables until the virtual outcome matches Hubble's images of similar mergers in distant galaxies. What's truly astonishing is how these simulations expose universal patterns, run enough collisions, and certain features like star-forming rings or elongated tidal tails emerge again and again, proving that behind the apparent chaos, there's an underlying order governed by physics. They've even solved long-standing mysteries, like why some merged galaxies become smooth ellipticals while others retain ragged spiral features. The answer often lies in the gas, too much, and the galaxy reignites with new stars, too little, and it settles into a featureless haze. Yet for all their power, simulations have limits. The sheer scale of galactic collisions where a single pixel in the model might represent hundreds of stars means small-scale details can get lost. That's where observatories like ALMA step in, peering through dust clouds to measure real gas motions, or the James Webb Space Telescope, spotting star clusters too young to exist in current models. Each new observation refines the simulations, tightening the spiral between theory and reality. So the next time you see a breathtaking image of colliding galaxies, remember, it's not just a still life. It's a frame from a cosmic film, one we're learning to reconstruct one simulation at a time. The stars scattered across a galaxy's halo aren't just random decorations, they're ancient storytellers whispering secrets of long-forgotten collisions. Like cosmic archaeologists sifting through stellar fossils, astronomers decode these narratives by measuring three critical clues: a star's age, its chemical composition, and the path it travels through space. Older stars forged in the early universe carry a distinct fingerprint their metal pore, lacking the heavier elements later generations would inherit from supernova explosions. Younger stars enriched by these cataclysms tell a different tale. By mapping where these populations cluster and how they move, scientists can trace their origins back to smaller galaxies torn apart and absorbed over billions of years. One of the most dramatic examples winds through our own Milky Way, the Sagittarius stream, a shimmering river of stars stretching across the night sky. This isn't just a random collection. It's the dismembered remains of a dwarf galaxy, once independent, now unraveling as our galaxy's gravity pulls it apart like cosmic taffy. The stars in this stream share nearly identical orbits and chemical signatures, a dead giveaway that they're outsiders, remnants of a galactic meal that began over 4 billion years ago. As the Sagittarius dwarf's core continues its slow death spiral, new stellar streams peel away with each pass, adding to the ghostly braids encircling our galaxy. But the Sagittarius stream isn't alone. The Milky Way's halo is littered with similar stellar rivers, the Gaia sausage, a mangled relic of a head-on collision 8 to 10 billion years ago. The Helmy stream, stars with wild, looping orbits hinting at another ancient merger, and even the mysterious Sequoia group, whose stars move in the opposite direction of most halo objects. Each of these structures is a chapter in our galaxy's autobiography, revealing how it grew not just from gas and dust, but by consuming smaller neighbors. What makes this galactic archaeology so powerful is how it transforms seemingly random stars into a coherent history. Take a single metal poor star orbiting backward in the halo. On its own, it's just an oddity. But when thousands of such stars are mapped by telescopes like Gaia, patterns emerge. Their shared motions and chemistries form stellar families, groups that clearly didn't originate in the Milky Way, but were adopted through violent mergers. Some families are so distinct, they still carry the kinematic signature of their original galaxy's dark matter halo, preserved like a fossilized shadow within our own. And this isn't unique to the Milky Way. Andromeda's halo shows even more dramatic evidence of past mergers, gigantic stellar shells, and colossal streams that suggest a history of galactic cannibalism far more violent than our own. The differences between their halos and ours may explain why Andromeda evolved into a slightly larger, more elliptical galaxy. Even distant galaxies, when studied with powerful spectrographs, reveal halo stars with conflicting origins, proving that growth through collision is universal. The real magic lies in what these stellar ghosts predict about the future. As astronomers identify more streams and reconstruct past mergers, they're building a playbook for how galaxies evolve, one that suggests our quiet Milky Way may have had a far more turbulent youth than we ever imagined. And when Andromeda finally collides with us billions of years from now, the resulting chaos will create new stellar streams, new families of stars, and a new chapter in the story that future galactic archaeologists will one day decode. The Whirlpool Galaxy and its smaller companion spin through space like a celestial waltz frozen in time, giving us a front-row seat to the earliest stages of galactic interaction. Catalogued as Messier 51, this stunning pair showcases how even a gentle gravitational encounter can spark dramatic transformation. The smaller galaxy, known as NGC 5154, isn't crashing headlong into its larger neighbor, it's gliding past, its gravity delicately plucking at the whirlpool's spiral arms like fingers strumming cosmic harp strings. The result, those magnificent, exaggerated arms, brimming with newborn stars that trace the paths of compressed gas clouds. This isn't destruction, it's gravitational artistry in progress. What makes interacting pairs like this so valuable is how they capture specific moments in a collision's billion-year timeline. The whirlpool shows us the opening act, where galaxies first begin reshaping each other. Compare this to the antennae galaxies, where twin tails of stars stretch halfway across the local universe, or the mice galaxies, their long tails still connected as they complete their first close pass. Each of these systems is a freeze frame in a cosmic flipbook, allowing astronomers to piece together the full story of galactic mergers by studying multiple examples at different stages. Zoom into the whirlpool's spiral arms, and you'll find clues to how these interactions fuel stellar birth. The smaller galaxy's gravity has stirred the whirlpool's gas reservoirs like a spoon swirling cream into coffee, creating dense pockets where star formation ignites. These regions glow an intense blue in telescope images, the signature color of massive young stars burning hot and fast, but the real magic lies in the details. Infrared observations reveal intricate dust lanes weaving through those arms, while radio telescopes detect vast clouds of hydrogen gas stretched into bridges between the two galaxies. Every wavelength of light tells part of the story. These galactic duos also challenge our assumptions about cosmic timescales. A human lifetime is too brief to witness meaningful change in such systems. The whirlpool's companion won't complete its first full orbit for another 500 million years. Yet through computer simulations that compress eons into minutes, we can fast forward through the entire dance. Models suggest that in about 100 million years, the companion galaxy will swing even closer, its gravity warping the whirlpool's disk into increasingly dramatic shapes before eventually merging completely. By comparing these predictions with real interacting pairs at later stages, astronomers test and refine their understanding of galactic evolution. Perhaps most remarkably, these cosmic laboratories demonstrate how sensitive galaxies are to even subtle gravitational nudges. The Whirlpool's companion is just 1/10 its size, proof that you don't need a catastrophic collision to reshape a galaxy, just time and the relentless pull of gravity. As we study more of these interacting pairs, from the stately elegance of the Whirlpool to the chaotic splendor of ARP 273's overlapping disks, we're reminded that in the cosmos, no galaxy is truly an island. Each gravitational encounter leaves its mark, whether in stretched spiral arms, tidal tails of exiled stars, or the brilliant flash of stellar rebirth, a testament to the universe's endless capacity for reinvention. When starburst galaxies ignite with the fury of 1,000 newborn suns, they don't just light up the cosmos, they reshape it with gales of unimaginable power. These galactic winds, born from the combined energy of supernova explosions and blistering radiation from massive young stars, blast outward at speeds exceeding thousands of kilometers per second. Picture a hurricane made not of air but of superheated gas laced with carbon, oxygen, and iron. The very elements forged in stellar furnaces, now being hurled far beyond the galaxy's original boundaries. The iconic starburst galaxy Messier 82 offers a textbook example where twin jets of ionized gas stretch over 30,000 light-years into intergalactic space, glowing eerily in X-ray observations like cosmic searchlights piercing the dark. What makes these winds so pivotal isn't just their spectacle, it's their dual role as both creators and destroyers. On one hand, they act as cosmic recycling plants, seeding the space between galaxies with heavy elements essential for future generations of stars and planets. The oxygen we breathe, the iron in our blood, much of it was likely forged in starburst galaxies and then scattered across the universe by these very outflows. Yet simultaneously, they're starving their home galaxies of the raw materials needed to sustain star formation. Like a wildfire that consumes its own fuel too quickly, these winds can effectively shut down a galaxy's ability to create new stars, leaving it to fade into a quiescent, aging state. Detecting these invisible tempests requires observing across multiple wavelengths. Radio telescopes reveal cold molecular gas being swept up in the outflow, while X-ray observatories like Chandra catch the telltale glow of million-degree plasma. Even ultraviolet spectrographs spot the fingerprints of these winds' absorption lines, shifted to bluer wavelengths as gas races toward us at phenomenal speeds. The Cartwheel Galaxy, still reeling from its bullseye collision, showcases all these phenomena simultaneously, with different instruments capturing different layers of its multilayered galactic gale. But here's the twist: these winds don't just blow in one direction. Recent observations suggest they often create vast feedback loops, where ejected material eventually cools and falls back onto the galaxy in a cosmic rain. The Phoenix Cluster's central galaxy exemplifies this cycle, where X-ray images show filaments of cooled gas plummeting back toward the galactic core, potential fuel for future star formation. It's a delicate balance: too much wind and the galaxy exhausts itself, too little and it might never disperse the heavy elements needed to enrich the cosmos. This self-regulating mechanism solves one of astronomy's long-standing puzzles: why we don't see more ultra-massive galaxies. Without galactic winds to limit their growth, mergers would create monstrous galaxies far larger than any we observe. Instead, these outflows act like a cosmic pressure valve, ensuring galaxies evolve within certain bounds. Even our Milky Way shows evidence of ancient winds in the chemical composition of its halo stars, a fossil record of past outbursts now woven into the galaxy's very fabric. As we study more of these galactic tempests, from the modest outflows of dwarf galaxies to the superwinds of merging behemoths, we're uncovering a universe where even the most violent events follow elegant patterns. The same forces that tear galaxies apart also spread the seeds for new beginnings, weaving an intricate web of matter and energy that connects every corner of the cosmos. Right now, we're witnessing the universe at its most creative, a time when galaxies collide in spectacular displays of gravitational artistry. But this era won't last forever. As the cosmos expands, carrying galaxies farther apart at ever-increasing speeds, the golden age of galactic mergers is quietly slipping away. Think of it like a grand cosmic party where the guests are slowly drifting to opposite corners of the room. Eventually, they'll be too far apart to interact at all. The driving force behind this cosmic separation is dark energy, the mysterious force accelerating the universe's expansion. Over the next 100 billion years, galaxies outside our immediate neighborhood will vanish beyond an unreachable horizon, their light stretched into invisibility by the relentless stretching of space itself. Already, astronomers observe this fate unfolding, distant galaxy clusters receding faster as the universe's expansion accelerates, leaving behind vast, ever-growing voids between them. The Milky Way and Andromeda's future merger will be one of the last great collisions in our cosmic vicinity, a final burst of creativity before isolation sets in. Even now, the universe is transitioning from its vibrant, collision-filled youth into a more solitary future, while galaxy clusters like our local group will remain gravitationally bound, allowing mergers like Andromeda to occur. Most galaxies beyond will never meet again. The Virgo cluster, for example, will continue cannibalizing smaller galaxies for eons, but eventually, even its feeding frenzy will slow as available neighbors dwindle. The universe's grand tapestry, once woven together by gravity, will gradually fray as dark energy pulls its threads apart. Yet this isolation won't mean stagnation. Galaxies left alone will continue evolving, their gas reservoirs slowly forming stars until they too fade. Elliptical galaxies, already red and aging, may become even more quiescent, while spirals like the Milky Way, if spared future mergers, could exhaust their star-forming fuel over hundreds of billions of years. The night sky from a planet in far future Andromeda would be strikingly different. No distant galaxies dotting the darkness, just the dim glow of aging stars in an island universe drifting through an ever-expanding void. What makes our current epoch so special is that we're positioned perfectly to witness both the fireworks and the silence. Telescopes today capture galaxies in every stage of collision, from first encounters to final mergers, while also revealing the first hints of the universe's lonely future. In a sense, we're cosmic time travelers, able to look backward at the universe's violent past and forward to its quiet destiny, all within a single lifetime of observation. So while the era of galactic collisions is finite, that very impermanence makes it all the more extraordinary. We're living in a moment when the universe still sculpts itself through gravity's patient hands, creating structures of breathtaking beauty before the curtain falls on this act of cosmic evolution. And long after the last galactic embrace, the echoes of these collisions will remain written in the motions of stars, the chemistry of planets, and the silent, enduring shapes of galaxies that once danced. Galactic collisions might seem like the ultimate cosmic catastrophe, a titanic clash where worlds are torn apart and life is snuffed out in an instant. But the reality is far more nuanced. When galaxies merge, their sheer scale becomes both a shield and a spectacle for any potential life nestled within them. Consider this: while these encounters trigger fireworks of star formation and flood space with intense radiation, the average distance between stars is so vast that planetary systems float through the chaos like ships passing in the night. Even as galaxies twist and intertwine, the odds of two stars colliding are astronomically low literally. Take our own Milky Way's impending merger with Andromeda. Simulations suggest that as the two galaxies spiral together, their stars will be flung into new orbits, but our solar system will likely drift through the turmoil unscathed. The real changes will be in the sky itself, where the familiar band of the Milky Way gives way to a dazzling scatter of stars as Andromeda's luminaries mingle with our own. For any civilizations watching, it would be a slow-motion light show spanning millions of years, with new constellations forming and fading like celestial clockwork. Yet there's a catch. While stars rarely collide, the surge of radiation from newborn stars in colliding galaxies could pose risks. Starburst regions like those in the antennae galaxies produce torrents of ultraviolet light and X-rays, enough to strip atmospheres from nearby planets. But here's the twist: life might thrive in the galactic suburbs far from these violent nurseries. Planets orbiting older, quieter stars could remain sheltered, their biospheres undisturbed even as the galaxy around them transforms. And then there's the question of timing. Galactic mergers unfold over billions of years, a timescale so vast that even the most resilient civilizations would likely rise and fall long before the final act. Imagine a species evolving on a world during the first close pass of two galaxies, only for their descendants to witness the merger's completion epochs later. The cosmic dance would be less a threat and more a backdrop to their history, written in the slow turning of the heavens. Perhaps most intriguing is how these collisions could actually nurture life. The heavy elements forged in merger-driven starbursts, carbon, oxygen, iron, are the same building blocks of planets and living organisms. Without past galactic encounters, the universe might lack the chemical diversity needed for life to arise at all. In this light, mergers aren't just destructive forces, they're cosmic catalysts stirring the galactic pot and scattering the ingredients for life across the cosmos. So while the idea of galaxies colliding sounds apocalyptic, the truth is far more poetic. These events are less about destruction and more about renewal, a reminder that even in the grand chaos of the universe, there's room for life to persist, adapt, and perhaps even thrive beneath skies alight with the artistry of gravity. If galactic collisions are symphonies of destruction and rebirth, then cluster mergers are the universe's grandest orchestras conducting energy on scales so vast, they dwarf even the mightiest galaxy collisions. The Bullet Cluster stands as astronomy's most famous example, a cosmic wreck where two galaxy clusters, each containing hundreds of galaxies, slammed together at speeds exceeding millions of kilometers per hour. The aftermath is a laboratory of extremes. Gas heated to over 100 million degrees glows in X-rays like a celestial forge, while the galaxies themselves sailed through the chaos nearly unscathed, their stars too sparse to collide. But the real revelation lies in what we can't see. Gravitational lensing maps reveal the cluster's dark matter halo's invisible scaffolding that plowed straight through the collision, leaving the visible gas behind like smoke trailing a bullet. This separation of dark and ordinary matter is one of cosmology's smoking guns, proving dark matter isn't just an abstract idea. It's a tangible, gravity-wielding substance that outweighs visible matter 5-1. Unlike gas, which slows and heats during collisions, dark matter's lack of interaction lets it coast through itself like ghosts passing through walls. The Bullet Cluster's dark matter maps, showing two distinct clumps ahead of the gas, perfectly match simulations of this collisionless behavior. It's as if the universe staged this cataclysm just to unveil its hidden architecture. Yet the energies at play here are almost incomprehensible. The merger released more energy in a few 100 million years than all the stars in the observable universe combined during that time. shockwaves rippling through the gas-created structures spanning millions of light-years, while turbulence generated magnetic fields strong enough to shape entire galactic ecosystems. Even the galaxies within the clusters felt the ripple effects, their orbits scrambled, their gas reservoirs stripped, their star formation rates altered for eons. What makes these events so pivotal isn't just their scale, but their rarity. While galaxy mergers happen frequently across cosmic time, cluster collisions are once-in-a-universe lifetime events for any given region. The Musket Ball cluster, a slower and older cousin to the Bullet cluster, shows us the later stages of this process. Its gas clouds have nearly finished recoalescing, while dark matter remains offset like a shadow lagging behind its source. By studying multiple clusters at different merger stages, astronomers piece together a timeline of these gargantuan encounters, revealing how they redistribute matter, energy, and even the heavy elements forged in stellar explosions across intergalactic space. And the implications stretch far beyond dark matter. These collisions act as particle accelerators of cosmic proportions, where shockwaves accelerate electrons to near light speeds, creating diffuse radio emissions that span entire cluster volumes. They are also the universe's ultimate pressure cookers, where gas heated to temperatures hotter than the sun's core emits photons that carry clues about the laws of physics under extreme conditions we could never replicate on Earth. As future telescopes like the European Space Agency's Athena X-ray Observatory come online, they'll peer deeper into these maelstroms, measuring gas motions with unprecedented precision and perhaps uncovering new dark matter mysteries. For now, the Bullet cluster and its kin remain towering reminders that the universe's most violent events often reveal its best-kept secrets, where gravity doesn't just shape galaxies, but bends the very fabric of reality to its will. Among the countless galactic collisions painting the cosmos, some defy expectations, entirely celestial train wrecks where the usual rules don't apply. The Taffy Galaxies, a pair known as UGC 12914 and 15, offer one of the most bizarre examples. Instead of gracefully spiraling toward a merger or flinging stars into tidal tails, these two galaxies barreled straight through each other like phantom freight trains, leaving behind a chaotic bridge of superheated gas stretching between them. This turbulent ribbon, glowing fiercely in radio wavelengths, isn't just debris, it's a snapshot of interstellar material caught in a gravitational tug of war, shredded and stretched by the galaxy's high-speed collision. What makes encounters like this so puzzling is how they upend our models of galactic behavior. Most simulations assume galaxies are surrounded by vast halos of dark matter, which should slow their approach and encourage a gradual dance. But the Taffy pair suggests some galaxies might slip through these halos like knives through smoke, their stars barely interacting while their gas clouds bear the brunt of the impact. The result, a luminous, mangled taffy pool of molecular hydrogen and dust, where magnetic fields have been amplified to extraordinary strengths, trapping particles in a turbulent whirlpool between the galaxies. Equally strange is the case of NGC 7752 and 7753, nicknamed the Atoms for Peace Galaxy. Here, one spiral galaxy speared another almost perpendicularly, its central bulge punching through the disk like a bullet through a spinning coin. The collision ignited a frenzy of star formation along the wound's edges, while shockwaves rippled outward, warping the victim galaxy's arms into a surreal, box-like shape. Unlike the stately mergers we often see, this violent encounter left one galaxy permanently disfigured, a reminder that not all collisions end in harmonious unions. Then there's ARP 148, the Mayol's object, where a smaller galaxy plowed into a larger one with such force that it triggered a shockwave of star formation in a perfect ring. Like a stone dropped in a pond, the impact sent waves of compressed gas rushing outward, igniting a stellar firestorm that now glows as a brilliant blue halo around the galaxy's core. These ring galaxies are cosmic oddities, their structures so precise they seem almost artificial, yet they're born from some of the most violent encounters imaginable. These outliers do more than just dazzle us, they force astronomers to rethink the physics of galactic interactions. Why do some collisions produce elegant tidal tails while others leave behind mangled bridges or perfect rings? The answers may lie in the speed of the impact, the angle of collision, or even the internal structure of the galaxy's dark matter halos. Each oddball merger is a puzzle piece, helping us refine our simulations and understand the full spectrum of galactic evolution. And perhaps most remarkably, these cosmic train wrecks remind us that the universe has a flair for the dramatic. Where we expect chaos, it sometimes delivers eerie symmetry. Where we predict gradual mergers, it offers high-speed collisions. Every distorted galaxy, every twisted bridge of gas, is a testament to the infinite variety of gravitational storytelling, a universe that never runs out of ways to surprise us. At the heart of every galactic merger lies a gravitational showdown between the most enigmatic objects in the universe: supermassive black holes. These cosmic behemoths, millions to billions of times heavier than our Sun, don't just passively observe as their host galaxies intertwine. They engage in a slow, inevitable dance toward one another, governed by the same forces that shape the collision. Yet here's the twist: while galaxies can merge within hundreds of millions of years, their black holes may take billions to finally unite. This staggering mismatch in timescales creates a surreal interim period where twin black holes orbit each other in a binary embrace, separated by just a few light years but unable to close the gap without help. Take NGC 6240, a mangled galaxy still reeling from a violent merger. Deep within its chaotic core, two supermassive black holes circle one another every 25,000 years, trapped in a gravitational standoff. They're close enough to warp spacetime around them, yet too distant to overcome their final hurdle, a problem known as the last parsec problem. Without a steady supply of stars or gas to steal their orbital energy, these black holes could remain locked in this cosmic limbo indefinitely. It's only when a third black hole or a dense cloud of gas enters the scene that the final plunge becomes possible, releasing a burst of gravitational waves powerful enough to momentarily outshine the entire universe. But the drama doesn't end with a merger. When two black holes finally collide, the resulting recoil can be so violent that the newborn black hole is kicked clear out of its galaxy. Imagine a cannon firing in zero gravity. The energy released during the merger isn't perfectly symmetrical, and the imbalance can launch the black hole at speeds exceeding thousands of kilometers per second. Astronomers have already spotted candidates for these rogue black holes, like the one in Galaxy 3C186, where a supermassive black hole appears to be fleeing its host, trailing a wake of glowing gas behind it. If ejected entirely, these nomads would drift through intergalactic space, invisible except for the faint glow of any trapped stars or gas still orbiting them. What makes these events so pivotal isn't just their spectacle, it's their role in solving one of astrophysics' biggest mysteries: how black holes grow so enormous. Early in the universe's history, supermassive black holes appeared far sooner than theories predicted, suggesting they didn't form solely by swallowing gas. Galactic mergers provide the missing piece, allowing black holes to bulk up by consuming their counterparts. Each collision is a growth spurt, with the final merger potentially doubling the black hole's mass in seconds. The gravitational waves from these events, now detectable by observatories like LIGO, carry fingerprints of the black hole's spins and masses, offering clues about their violent past. Yet, even as we unravel these processes, new questions emerge. How often do recoiling black holes escape their galaxies? Can a galaxy function without a central black hole? And what happens to the stars and gas left behind when their gravitational anchor vanishes? Each merger is a cosmic experiment, testing the limits of gravity and revealing how the universe's most extreme objects shape the galaxies around them, proving that even in the darkest corners of space, nothing stays still forever. Peering deep into the cosmos isn't just about observing the present. It's a form of time travel, where light becomes our window into the universe's violent, creative past. Telescopes like Hubble, the James Webb Space Telescope, and ALMA act as cosmic historians, each specializing in different chapters of galactic evolution. Hubble's sharp eye captures the visible aftermath of collisions' tidal tails stretched across millions of light years, galaxies frozen mid-embrace. JWST infrared vision pierces through dust to reveal the fiery nurseries where mergers ignite star formation, while ALMA radio antennas trace the cold molecular gas fueling these stellar explosions. Together, they form a multi-wavelength detective team, reconstructing galactic mergers across billions of years. The further back we look, the more dramatic the collisions become. In the early universe, galaxies were smaller, denser, and swimming in primordial gas-perfect conditions for chaotic mergers. The cosmic dawn galaxy GNZ 11, observed by JWST just 400 million years after the Big Bang, already shows signs of gravitational disturbances, as if it's being twisted by unseen companions. These ancient mergers weren't just more frequent, they were fundamentally different. Gas-rich and turbulent, they triggered starbursts so intense they could outshine modern galaxies by 100-fold. The Sparkler Galaxy, another JWST discovery, contains globular clusters likely born from such a collision, stellar fossils preserving the fingerprints of the universe's first mergers. What's astonishing is how these ancient encounters shaped galactic evolution. While today's mergers are relatively rare events, in the early universe they were the rule rather than the exception. The Spiderweb Galaxy, a chaotic protocluster observed 12 billion light-years away, shows dozens of smaller galaxies being drawn into a gravitational web, their gas streaming behind them like cosmic comet tails. These collisions didn't just build galaxies, they built the very scaffolding of the universe, with supermassive black holes growing in tandem through each merger. Modern observations also reveal an unexpected pattern, the downsizing of cosmic collisions. As the universe expanded and galaxies grew farther apart, mergers became less frequent but more targeted. Giant ellipticals like Messier 87 didn't form from one dramatic collision but from dozens of smaller, carefully timed mergers, a slow accumulation of mass that continues today. Even our Milky Way is quietly consuming the Sagittarius dwarf, a process that began billions of years ago and will continue for billions more. The real power of these observations lies in their ability to test our theories. Simulations of galaxy formation, when compared to real merger snapshots across cosmic time, must account for everything from the gas dynamics of early starbursts to the dark matter distributions in modern clusters. Discrepancies between models and observations, like the surprising number of thin, disc-shaped galaxies surviving in the early universe, force astronomers to refine their understanding of how gravity, gas, and dark matter interact. And the story isn't complete. Upcoming telescopes like the Nancy Grace Roman Space Telescope will map millions of galaxies, catching mergers in every stage of cosmic history. The extremely large telescope, with its 39-meter mirror, will peer into galactic cores to watch black holes dance. Each new instrument adds another piece to the puzzle, revealing how these gravitational ballets have shaped everything from the smallest dwarf galaxies to the largest superclusters, a reminder that the universe's history is written not just in stars, but in their collisions. There's an undeniable artistry to galactic collisions, a visual poetry where the rigid laws of physics yield breathtaking beauty. Picture the Whirlpool Galaxy, its spiral arms streaked with sapphire star clusters and crimson dust lanes, each curve a brushstroke painted by gravity's invisible hand. Or the Cartwheel Galaxy, its perfect ring glowing like a cosmic halo, a momentary symmetry born from chaos. These aren't just scientific phenomena, they're celestial masterpieces where gas and dust become the palette and gravity the artist. The colors alone tell a story. The deep blue hues of young, massive stars, scattered like splattered paint across tidal tails, contrast with the rusty red of ancient stellar populations. In the antennae galaxies, neon pink hydrogen clouds pulse with the energy of newborn stars, while filaments of golden dust weave through the chaos like threads in a tapestry. Even the blackness between stars plays a role, carving negative space into the composition. It's no wonder these scenes inspire astronomers and artists alike, bridging the gap between data and dreams. But the beauty isn't just in the broad strokes. Zoom in, and you'll find fractal-like patterns, tiny star-forming regions mirroring the grand arcs of the galaxies themselves. The delicate filigree of dust lanes in NGC 4676, backlit by the glow of its core, resembles ink swirling in water. The overlapping disks of ARP 273 create optical illusions, their warped perspectives tricking the eye into seeing depth where there's only vacuum. These aren't accidents, they're the universe's way of reminding us that even in destruction, there's design. Human creativity has long drawn from this cosmic wellspring. Van Gogh's Starry Night, with its swirling skies, eerily echoes the turbulence of interacting galaxies. Modern digital artists use Hubble images as backdrops for sci-fi landscapes, while composers translate infrared data into ethereal soundscapes. Even NASA visualizations where supercomputer simulations become swirling films blur the line between science and art. The irony is delicious. The same equations that describe galactic collisions also shape the brushstrokes of those who paint them. Perhaps what's most striking is how these events challenge our sense of scale. A single pixel in a Hubble image might contain thousands of stars, yet the overall structure feels intimate, almost organic. The tendrils of the mice galaxies could be veins under a microscope or rivers seen from space, a reminder that the universe repeats its patterns across dimensions. And in that duality, where the unimaginably vast feels strangely familiar, lies the true magic of these collisions. They're not just transforming galaxies, they're redefining how we see our place in the cosmos, one radiant, chaotic frame at a time. Long before astronomers mapped the heavens with precision, our ancestors looked up and wove stories from the stars, some of which may hold hidden truths about galactic collisions. The Andromeda Galaxy, visible to the naked eye as a faint smudge in the constellation bearing its name, appears in myths from Persia to Polynesia. In Persian astronomy, it was called the Little Cloud, while Maori traditions describe it as a celestial anchor holding the Waka of Tamareti in place. Could these descriptions be ancient eyewitness accounts of our galaxy's future dance partner? It's a tantalizing thought that cultures separated by oceans and millennia might have unknowingly recorded the first hints of a cosmic destiny written in starlight. These celestial encounters have always sparked the human imagination. The Japanese legend of Tanabata tells of two star-crossed lovers, Vega and Altair, separated by the Milky Way, a poetic echo of galaxies drifting apart only to reunite. Indigenous Australian Dreamtime stories describe the emu in the sky, its dark silhouette formed by dust lanes in our own galaxy, a reminder that even the most ancient stargazers saw motion and drama in the night. Today, that tradition continues in modern sci-fi, where galactic collisions become backdrops for epic tales. From the dying worlds of The Three-Body Problem to the cosmic rebirths in Doctor Who, these events symbolize both catastrophe and transformation, mirroring humanity's own fears and hopes. Artists, too, have long drawn inspiration from the chaos and beauty of colliding galaxies. Van Gogh's turbulent skies in Starry Night seem to presage Hubble's images of swirling galactic arms, while contemporary creators like David A. Hardy paint luminous mergers with a detail that blends science and surrealism. Even music captures their rhythm. The symphonic metal band Nightwish composed The Greatest Show on Earth as an ode to cosmic evolution, its crescendos mirroring the violent grace of galactic encounters. These creative interpretations aren't just tributes, they're bridges, translating the cold equations of astrophysics into something visceral and emotional. Perhaps most remarkably, these collisions challenge our perception of time. A single merger unfolds over epochs longer than human history, yet cultures across the ages have glimpsed fragments of the process, whether in myth, art, or the silent awe of a dark sky. Today, as telescopes reveal the intricate choreography of galaxies like never before, we're not just observers of these events, we're participants in a story that began billions of years ago. The same gravitational forces that sculpted the Whirlpool galaxy or the antennae are still at work, patiently weaving the next chapter, one that future civilizations might one day recount in their own myths and melodies. The next era of galactic exploration is already dawning, with revolutionary telescopes poised to rewrite what we know about colliding galaxies. The Vera Rubin Observatory, set to begin its legacy survey of space and time in 2025, will scan the entire southern sky every few nights, capturing the faintest tidal tails and warped galactic disks that previous surveys missed. Imagine an ultra-high-resolution time-lapse of the universe, where millions of interacting galaxies are caught mid-collision, their transformations documented frame by frame over a decade. This isn't just about spotting more mergers, it's about watching them evolve in real cosmic time, tracing how tidal forces reshape galaxies across different stages of interaction. Meanwhile, the Nancy Grace Roman Space Telescope will peer deeper into infrared wavelengths, cutting through the dust that obscures galactic cores to reveal the fiery hearts of mergers. Its wide-field camera could uncover thousands of hidden ultra-luminous infrared galaxies, those cosmic powerhouses currently shrouded in debris, while simultaneously mapping the intricate webs of dark matter that guide these collisions. Together with JWST Sharp Infrared Vision, these observatories will create a three-dimensional atlas of galactic encounters, showing not just where mergers happen, but how their environments, whether in dense galaxy clusters or isolated voids, shape their outcomes. But perhaps the most groundbreaking discoveries will come from gravitational wave astronomy. While current detectors like LIGO catch the mergers of stellar mass black holes, future space-based observatories like LISA, the Laser Interferometer Space Antenna, will tune into the lower frequency ripples from supermassive black hole collisions. These events, 1,000,000 times more massive than anything LIGO can detect, will reveal how black holes spiral together in the final moments before merging, whether they stall in cosmic standoffs or plunge directly inward. Some theories suggest these mergers might produce frequencies so distinct they could serve as standard sirens to measure cosmic distances with unprecedented precision. The data floodgates are about to open, promising answers to long-standing mysteries. Why do some mergers produce elliptical galaxies while others retain spiral features? How often do supermassive black holes get ejected from their galaxies post-collision? And could gravitational lensing of these events, where space-time bends their light into multiple images, help us map dark matter's distribution? Each observation will be a puzzle piece in understanding how galaxies grow, evolve, and occasionally cannibalize each other in the cosmic dance. What makes this moment so thrilling is how these tools complement each other. Rubin's sweeping surveys will flag strange galactic morphologies for Roman's sharper eyes to investigate, while LISA gravitational wave alerts might prompt JWST to zoom in on merging black holes. It's a new age of multi-messenger astronomy, where light, gravity, and time itself become lenses to view the universe's most spectacular transformations. And somewhere in that deluge of data, we may find surprises that rewrite our cosmic playbook entirely, proof that even in the well-trodden subject of galactic collisions, the universe always keeps a few secrets in reserve. Gazing up at the night sky with nothing more than a modest telescope, you can witness the same galactic ballets that captivate professional astronomers' cosmic interactions frozen in time, their light traveling millions of years to reach your backyard. The Whirlpool Galaxy, known as Messier 51, is one of the easiest targets for amateur observers, its spiral arms visibly distorted by the gravitational tug of its smaller companion, NGC 5154. Under dark skies with an 8-inch aperture telescope, you'll see their connection, a delicate bridge of starlight stretching between them, a snapshot of a slow-motion embrace that began 500 million years ago. For those seeking more dramatic collisions, the antennae galaxies in the constellation Corvus offer a stunning example of a merger in progress. Though fainter than the Whirlpool, they reveal their tangled structure through a 6-inch or larger telescope, their twin tails of stars fanning outward like celestial fireworks caught mid-explosion. Patient observers might even spot the telltale glow of star-forming regions, knots of blue-white light where compressed gas ignites new stellar births. And don't overlook the mice galaxies in Coma Berenices, their long, slender tails stretching across the eyepiece like cosmic brushstrokes, a testament to the gravitational forces sculpting them over eons. The thrill of observing these galaxies isn't just in their beauty, it's in the realization that you're witnessing events unfolding on timescales beyond human comprehension. That faint smudge of light in your eyepiece, it left its galaxy when Earth's continents were still arranging themselves into unfamiliar shapes. To observe merging galaxies is to become a time traveler, peering into a past where dinosaurs roamed or ice ages gripped the planet, all while the light you see tonight journeys toward some future observer's telescope. Enhance the experience with astrophotography, where even basic DSLR cameras can capture the ethereal glow of these interactions. Long exposure shots reveal details invisible to the naked eye, the delicate filaments of tidal tails, the warped disks of colliding spirals, the subtle hues differentiating young blue stars from ancient red giants. Online communities like AstroBin or the Cloudy Nights forums buzz with amateur contributions, proving that cutting-edge cosmic discovery isn't confined to mountaintop observatories. What makes these observations so profound is their power to shrink the universe down to a human scale. When you locate the Whirlpool or the antennae in your eyepiece, you're not just checking off objects on a list, you're participating in a lineage of curiosity that stretches back to Galileo. You're seeing the same forces that will one day reshape our Milky Way, a reminder that the cosmos is neither static nor distant, but a living, evolving tapestry we're woven into. And with each clear night, another chapter of that story becomes visible, waiting just beyond the reach of city lights. galactic collisions spark dramatic mental images, stars slamming together in cosmic car crashes or entire galaxies vanishing into oblivion. But the reality is far more fascinating and less destructive than our imaginations suggest. One of the most persistent myths is that mergers send stars careening into one another like billiard balls. In truth, the average distance between stars is so vast that our entire solar system could pass through another galaxy with near certainty that not a single star would collide. Picture two swarms of bees flying through each other in an empty stadium. The individual insects zip right past one another without touching. That's how galaxies interact, their stars drifting through the void like ghosts, barely noticing the encounter. Equally misleading is the idea that mergers erase galaxies from the cosmos. While their structures transform dramatically, the outcome isn't destruction, it's reinvention. Take the Milky Way's impending merger with Andromeda. Far from annihilating both galaxies, their collision will birth a new, larger elliptical galaxy astronomers call Milky-Way. This cosmic offspring will inherit stars from both parents, its night sky ablaze with twice as many stellar points of light. The process mirrors how raindrops merge in a puddle, individual identities blend, but the water itself persists, reshaped into a new form. Some assume these events unfold quickly, like a Hollywood explosion. In reality, galactic mergers are the ultimate slow-motion spectacle. A single close pass between two galaxies can span hundreds of millions of years, with multiple orbits required before they fully coalesce. Humanity's entire existence, from stone tools to space telescopes, amounts to a blink in this timescale. The antennae galaxies, for example, began their dance over 300 million years ago, back when Earth's dominant life forms were early reptiles, and they're still mid-collision today. Another common oversimplification casts mergers as uniformly violent. While some trigger ferocious starbursts, others unfold with surprising gentleness. The Whirlpool Galaxy's interaction with its smaller companion has stretched its spiral arms into stunning patterns without the chaotic disruption seen in head-on collisions. Even in more dramatic mergers, the turbulence often remains confined to specific regions, leaving vast swaths of each galaxy relatively undisturbed. It's less like a demolition derby and more like a complex dance where partners occasionally step on each other's toes. Perhaps the most poetic correction to these misconceptions lies in the creative power of collisions. Far from being purely destructive, mergers are the universe's way of recycling and renewing. The same gravitational forces that warp galaxies also compress gas clouds, igniting new stars and dispersing heavy elements essential for planets and life. Without past mergers, our Milky Way might lack the chemical diversity that made our solar system possible. These events aren't endpoints, they're turning points in an endless cosmic story of transformation. So the next time you see an image of colliding galaxies, remember, you're not looking at a catastrophe. You're witnessing the universe's grand workshop where gravity sculpts, reinvents, and occasionally, with perfect patience, redraws the celestial map. The vast timelines of galactic collisions stretch far beyond human intuition, where a single merger can outlast the entire existence of complex life on Earth. To grasp these eons, astronomers employ a cosmic version of time-lapse photography, studying thousands of interactions frozen at different stages, from first gravitational flirtations to final embraces. The Tadpole Galaxy, with its 300,000 light-year-long tail, represents adolescence in this life cycle, a snapshot of a smaller galaxy recently torn apart by a larger neighbor. Meanwhile, NGC 7752 and 7753 showcase middle age, their distorted shapes locked in a slow-motion duel that's already lasted 100 million years. And ancient ellipticals like Messier 87, they're the silver-haired elders, their smooth profiles hiding violent merger histories billions of years past. This cosmic detective work reveals patterns invisible to any single observer, just as a single frame of a blooming flower tells you nothing about its growth. A snapshot of one collision misses the grand narrative. But line up enough examples from the early tug-of-war in the Whirlpool Galaxy to the fading embers of Starburst activity in the Mice Galaxies, and suddenly, the process unfolds like pages in a flipbook. Computer simulations then breathe motion into these still images, calculating how gravity, gas dynamics, and dark matter conspire to stretch eons into comprehensible animations. Watching these models, we discover how tidal tails grow like celestial taffy, how galactic cores ignite with starburst fireworks, and why some mergers leave behind elegant rings while others become featureless blobs. What's humbling is realizing how much we miss by living in cosmic blink. The antennae galaxy's current fireworks began when dinosaurs still roamed, and their merger won't finish until Earth's continents rearrange into new supercontinents. Yet this glacial pace is precisely what allows for such intricate transformations. Gravity's gentle tug, persistent over millions of years, can sculpt gas clouds into stellar nurseries without tearing them apart. Stars flung into tidal tails have time to find new orbits, like dancers gradually shifting positions in a ballroom. Even the supermassive black holes at galactic centers need these vast stretches of time to negotiate their final spirals, shedding energy through gravitational waves until they collide. And here's the twist: while individual mergers are slow, their cumulative effect shapes the universe. Just as seconds add up to lifetimes, these collisions built the galactic giants we see today. The Milky Way's halo, littered with stellar streams from past meals, proves even our peaceful spiral has a violent history. Each merger leaves chemical fingerprints, generations of stars enriched with heavier elements, then scattered like seeds across the cosmos. Without these patient, eons-long dances, galaxies would remain small and barren. Their gas reservoirs never stirred enough to spark the diversity of stars and planets we know. So when we marvel at Hubble's images of colliding galaxies, we're not just seeing chaos, we're glimpsing chapters in a story where time itself is the protagonist. A story where patience isn't just a virtue, but the fundamental force rewriting the cosmos. Galactic collisions are the universe's ultimate alchemists, transforming chaos into dazzling new forms through nothing more than the patient pull of gravity. These encounters aren't random accidents. They are fundamental chapters in the story of how galaxies grow, evolve, and sometimes even give birth to entirely new cosmic structures. Consider the humble hydrogen atom, drifting quietly through space for billions of years until a galactic collision compresses it into a blazing new star. The gold in your jewelry, the oxygen in your lungs, these elements were forged in the fiery hearts of stars born from similar violent encounters. Every time we study these collisions, we're not just observing distant events, we're glimpsing the very processes that made our existence possible. What's truly remarkable is how these collisions balance destruction with creation. The same gravitational forces that tear galaxies apart also trigger the birth of millions of stars, illuminating the cosmos with their brilliance. Starburst galaxies like Messier 82 shine as beacons of this paradox, their furious star formation rates powered by the same chaos that distorts their shapes. Even the supermassive black holes at their cores, locked in deadly spirals, eventually merge to form even larger gravitational anchors that will shape their galaxies for eons to come. It's a cycle as old as the universe itself, endings becoming beginnings, loss giving way to renewal, and this isn't just happening in some far-off corner of space. Our own Milky Way is a living testament to this process. its halo littered with the remnants of smaller galaxies it has absorbed over billions of years. The Sagittarius dwarf spheroidal, once an independent galaxy, now exists only as a shimmering stream of stars orbiting our own, a cosmic fossil telling the story of our galaxy's growth. Soon, Andromeda will add its own chapter to that story, merging with the Milky Way to create a new galactic masterpiece. Future civilizations, if they exist, will gaze up at a sky filled with unfamiliar constellations, the legacy of this slow-motion dance written across the heavens. Yet for all we've learned, these collisions still hold mysteries. Why do some mergers produce elegant rings while others become turbulent maelstroms? How do supermassive black holes finally overcome the last parsec problem to merge? Each new observation, each advanced simulation peels back another layer of the puzzle. Upcoming telescopes like the Vera Rubin Observatory and LISA will push our understanding even further, revealing details about dark matter's role in these collisions and capturing the gravitational waves from black hole mergers with unprecedented clarity. The more we discover, the clearer it becomes. Galactic collisions aren't just events in space, they're the universe's way of moving forward. So the next time you see an image of the antennae galaxies or the whirlpool's twisted arms, remember, you're not just looking at a momentary spectacle. You're witnessing the universe's grand, iterative process of reinvention. From the tiniest dust grain to the mightiest black hole, everything is part of this cosmic dance, forever changing, forever evolving. And as we continue to explore, we're not just mapping the stars, we're learning how to read the story they tell, one collision at a